Let's imagine that we start out with some unpolarized light with an intensity of S. Now remember, unpolarized light meaning the waves are oscillating all over the place, up, down, back and forth, every direction. But remember, it's in this plane that it's oscillating in every direction because it has to be perpendicular to that direction, which is the direction of the velocity. So the electric field can only oscillate up and down and in and out of the board. It can't oscillate in this direction, this way or this way. So we've got an unpolarized light with an initial polarization of, an initial intensity of S. That light then passes through a polarizer that, let's say, is oriented vertically. We then end up with polarized light, and let's say the intensity is now S prime. How is S prime related to S? We'll come back to that in just a second. But the important thing is, when the light passes through this polarizer with a vertical polarization, our light is now polarized in the vertical direction. Once light passes through a polarizer, it is then polarized in the direction of the polarizer. Now let's imagine we have a second polarizer, which is tilted at an angle. Now really we'd be looking this way. The new polarizer is, let's say, tilted at an angle of theta relative to the first polarizer. So we're looking this way. Here's the initial polarization, and then the new polarization, let me use a bigger one. The new polarization is tilted at an angle of theta relative to the first polarizer. But remember, we're looking in this direction. So from the initial direction, it's now tilted an angle of theta. How much light will make it through that second polarizer? In other words, let's assume that our new intensity, once it gets through, is some intensity S prime, S double prime. How is S double prime related to S prime? Well, let's remember, only, let's say the electric field, only that amount of electric field that is pointing in our new polarization direction will make it through. Well, let's say we have an electric field of, well, let's call this, say, E prime. E prime, that's the electric field of the light for S prime. Only the component of E prime that's along our new polarization will make it through. Well, how much is that? If the new polarizer is tilted at an angle of theta relative to our first polarizer, only a component of E prime cos theta will make it through. The electric field is going to be cut down by a factor of cos theta. However, remember, intensity goes like the energy density, and the energy density goes like the electric field squared, and the magnetic field squared. So if the electric field drops down by a factor of cos theta, the intensity will drop down by a factor of cos squared theta. There we go. What we have is then that S double prime will equal S prime times cos squared of theta. When polarized light passes through a second polarizer, the intensity is cut down by a factor of cos squared theta, where theta is the angle between the original polarization and the new polarizer. This result is called Malice's law. Excellent. This tells us how polarized light is cut down by a factor when it goes through a new polarizer. Back to our first question. Well, what happens when the light is unpolarized? How much light makes it through then? Well, this is a good question because originally the electric field is oscillating all over the place. So it's not all at one angle to the original polarizer. We could have an angle of 0, we could have an angle of 90 degrees, we could have an angle of anywhere in between 0 and 90 degrees, or 180 degrees. What we have to do is then actually find what's the average of cos squared. But we already know that. We've already taken an average of sine squared, and it's the same as the average of a cos squared. The average of cos squared is how much? 1/2. So when unpolarized light passes through a polarizer, only half of the intensity makes it through. So what we have is that S prime is 1/2 of S. Very, very good. When unpolarized light passes through a polarizer, we get 1/2 of the original intensity making it through. But when polarized light passes through a second polarizer, the intensity is cut down by a factor of cos squared theta, where theta is the angle between the original polarizer and the second polarizer. Very, very good. Let's stick some numbers in here. Let's imagine we have an initial polarization of our unpolarized light of an intensity of 0.750 milliwatts per millimeter squared. This is maybe like an intensity for a laser or something like that, a laser pointer, where we've got a power in milliwatts and an area of per millimeter squared, so a square millimeter. 0.750 milliwatts per millimeter squared. We then send that through a polarizer. Let's say the polarization is vertical. The direction doesn't matter. What's the intensity of the polarized light after it goes through the polarizer? Well, we know S prime is 1/2 times S, the unpolarized light, 1/2 times 0.75 or 0.375 milliwatts per millimeter squared. Now let's send that polarized light through a second polarizer, and let's imagine that the second polarizer is tilted at an angle of 20 degrees to our first polarizer. How much light makes it through? Well, we know S double prime equals S prime cos squared theta, or 0.375 times cos squared 20 degrees, 0.331 milliwatts per millimeter squared. Very good. Let me just ask you something else. I just want you to think about this. We have a polarizer with a polarization that is vertical. And we then take that light through that polarizer and we put it through a polarizer which is horizontal. How much light will make it through that second polarizer? In other words, what is theta? Well, theta is 90 degrees. What is cosine of 90? It's 0. So how much light will make it through that second polarizer? None. Cos 90 is 0, cos squared 0. So we have the light coming through, polarized vertically, vertical light trying to make it through a horizontal polarizer, 0 light gets through. That's what we have in this case. If I arrange these two polarizers so that their orientation is perpendicular. Light that goes through one cannot make it through the second, and 0 light makes it through. However, what if we were to put a third polarizer in here? What if we were to put a polarizer in here at an angle of 45 degrees from the first one, which is then 45 degrees from the second one? Would any light make it through after all three polarizers? So no light makes it through when we have two polarizers. Can putting a third polarizer in there actually get some light through? Well, this is a very interesting question. Let's imagine that we have our original intensity over here of S. How much makes it through the first one? 1/2 S. How much makes it through the second one? Well, we have to take this intensity multiplied by cos squared. What's theta? Theta is 45. So we have 1/2 S, 1/2 S cos 45 degrees squared. But now the polarization is at an angle of 45 degrees. How much will make it through the next one? Well, what's the angle from this one to the polarized light that's actually going through? It's only 45 degrees. So the amount that makes it through over here will be this intensity, which is here, times cos squared 45 degrees. We will end up with 1/2 S cos to the 4th of 45 degrees. That's smaller, but it's not 0. So by putting in an additional polarizer, we can actually increase the amount of light that makes it through. That sounds like a very, very strange result, but we can actually demonstrate it. Here, I've got my two polarizers, and I hope you can see here that there is no light making it through. So when they are in the same direction, theta would be 0 and cos 0 is 1. We have the same amount making it through one as through the second. But if I align these perpendicular, then we get no light making it through. I'll try and get these just perpendicular. And here I have another polarizer. If I put this behind or in front, we get no change. But what if I put this in between and align it just right? I hope that you can see there's actually some light that's making it through all three. Now, the light doesn't make it through two, but when I've got one in between, then some light does make it through. Very, very interesting. Well, what if rather than one that was at 45 degrees and 45 degrees to the next, what if we put in two? One at 30 degrees and then one at 60 degrees? Or what if we put in three or four more or five more or six more? What would happen? How much light would get through? Very, very interesting question. See if you can figure that out. I think that's a very interesting result. If you get the answer, I think you might be surprised. Well, I hope that was interesting. I hope you enjoyed it. Next time, actually, what are we going to do next time? I think I know, but let me just check. Right. Next time, sorry about that. Next time, we're going to start to look at what happens when light actually hits reflective surfaces, like mirrors. We're going to see some very, very interesting results. All right, well, look forward to that. I'll see you next time.